Hi again. We'll continue our work on life annuities, and we are still in the continuous case of life annuities. So last time we looked at whole life annuity, so it's like a pension that it stops at time of death. Now we have a variety of other life annuities, continuous cases, but we'll start looking at a life annuity that it pays for a certain period, or we'll look at later on that it starts at later period or other variety. So let's start with the case that you have, like let's say an individual age X, and the individual age X buys an annuity, life annuity, that it pays as long as the person is alive. It will pay $1 a year, or 1 unit of insurance a year, paid continuously up to the period N, right? And up to the period N, and after that there is no payment, right? So we will see. So this is the period that we're looking at. This one, if you would look at the random variable here, or the present value here, what the individual will get is that if death occurs here, so if death occurs here, the individual will get the annuity. Maybe I'll keep it this color so we recognize the annuity up to time of death, that stops at moment of death if death occurs between X and X plus N. But now if death occurs greater than N, if death occurs greater than N, somewhere here, or in other words, if the individual survived to this period, would have accumulated all the insurance of A bar N, right? Because he survived to here, so he collected, or she collected, the annuity that pays $1 for every year of the N period, because he survived. If death happens anywhere, if it's less than the N, if death happens in the green area, we'll get the insurance up to the moment of death, right? And this, what we call it, like this type of annuity, is N year. So because it's a period N year, temporary N-year temporary life annuity. Or sometimes we just shorten it temporary annuity, temporary life annuity, right? So it's N-year temporary life annuity. So in actuarial science, we always like the actuarial present value. So this is already like the present value, right? Here. So we take the actuarial present value. Remember, we take the expected value of the payment, or usually because we still in the continuous case, we integrate. We have two parts here, right? We need to be careful about the two parts here. We have N up to N, right? So for the first period, we take A, the green one, A T, right? With the f of t, TPX. Mu x plus t dt. This is the first period, plus this is for the first term. Now for the second term, this one is kind of, it depends on survival, right? So now we get this amount, A N, right? You get the present value, and now we need the f of t, right? So remember, this is like f of t, or not the f of t for our case for an, it's the like the survival. We don't need to integrate. It's either you get it or you don't get it. So if the person survive npx, if the person npx surviving the period n, will get this amount, right? So either you get this one or you get this one, right? So if survival happens, you get a bar n, angle n, or if death happens before, you get this annuity, right? It makes sense, makes a lot of sense. But this is, if you want to do the integration, but we need the notation for this one. Actually, there is a notation for this one, as you would expect It's not gonna be a new notation. Now we know once we see a small letter, it tells us it's annuity. There is a bar on any notation. It tells us that this bar is continuous. And X is the age X, where the insured, like issued the insurance. Now we have angle N. There is no one here, just without one, because this is annuity. It's not right, this notation. So again, what it tells us, a small letter, it tells us that this is annuity. There is a bar on top of it. It tells us it's continuous. The X is the age, as always. The angle is the period of the temporary, the N year, right? So there we can simplify also this one with relationship with insurance is 1 minus A capital. What is A capital? Always it's the insurance, X, N, divided by delta. And this is very important, obviously, very, very important relationship. Wanted you to see there is no one here, right? There is no one here, right? I want you to see this is the pure endowment, not the pure endowment, the endowment insurance. This one, endowment. And this one is AX. N plus need to be very careful about this AX, because if it's if it's not calculated, you need to calculate the term it by yourself. Let's take one example here. Let's take this example. And the example, it goes that X is uniform. Just as for simplicity 0 to 100, like the X is the remaining life random variable, and delta, the same example, 0.5%. We've taken this example many times. So the question is find a bar 30 for 10 years, right? This is very simple, straightforward. This one should be very simple for us. Why? Because we can apply the first rule here. 1 minus, oh sorry, there is a bar here, sorry. There is a bar. Corrected, there is a bar here. Okay, please correct this one, there is a bar. So anyway, this one will be 1 bar 30, 10, divided by, remember, we need delta. Right, let's take one by one. Now we need this one separately here. A 30, 10 plus 10E 30, right? So now we take this one separately now, A30 for 10 years. You go back to your notes on this on the insurance benefit, and this is easy because this is uniform distribution. It tells us it's uniform distribution, right? So for uniform distribution is 1 over omega minus x, which is 1770, and then we take for the 10 years. And this you can calculate it quickly, 70 and 1 multiplied by 1 e minus delta 10 divided by delta. If you calculate this one, I already calculated for you. This one, well, maybe I didn't calculate it. Yeah, I did actually. 0.11224. And this is, you go back to the notes you already calculated before, right? It's the same notation. Now, what is the second term here? This one, 10E30 is, remember, it's E minus delta multiplied by 10 multiplied by TP30. TP30 for TP30 it's for uniform distribution. TPX, if you write it on the side for this distribution, will be 70 minus T divided by 70. Those you need to do them quickly. You don't need to really even write it, because you should know about this. 70 minus 10 is 60 divided by 70 is 6 over 7. And this one should give us 0.5199. Again, like those, we've done them many times. By now you should calculate quickly those like TPX, E to lambda, all those kind of variables. Now you have this one and you have this one, so you can compute this one to be if you calculate this one, it will be 6323, right? Because you have the two terms. Now you have everything to calculate this one, right? So it's 1 minus 0.6323 divided by delta, which is, we said what was delta, is 5%, right? It's, I got 7354. And this is the answer. So you need really to be organized, very careful. First thing, you write your equation and then see what is missing. You start with the answering the question right away. See what's missing, and then try to split it out. Spell it out and see what is, if you have all components. If you don't, then you calculate them and you move on. This is very important to be organized while you're doing problems like this. Right. Another annuity that is also a possibility, that annuity is deferred annuity. Deferred annuity. Let's say for insurance, so the deferred annuity that will start at age of, let's say, 65. So for somebody is younger, would know that they will receive a stream of income, life annuity, at time of retirement. So it starts at time of retirement and continues until death. So now we have an X. Let's take this one. It's called N-year deferred annuity, life annuity, of course. So the story, you have X plus N. Somebody may be age 30 and would start getting a retirement stream of income at age 65 or 67 or whatever the year. And then the insurance happens here. There is $1 paid continuously, and let's take the continuous case. We're still in the continuous case, and not H, it's an N, right? So we need to evaluate this insurance. Very simple. It has a notation, shouldn't be a surprise. You have an N, and there is little bar here, and then because we're dealing with annuity is A, and it's continuous case, there is a bar, and evaluate it at age X, right? So this one, you can write it in different ways, right? It's if you would think about it, that starts, if like you can do the general form, because it's you evaluate from 0 to infinity, VT TP. Well, you can write the same notation. Let me just make sure that I give you the correct notation here. You know what, let's not do the integration. This one is straightforward, right? Because it's straightforward. We already know AX plus N here, right? So we can write, let me write it down here. So we have N, A, N, A, X, and we need here, because they are different time zone or different time in the horizon. So we need to get this one, which give you the stream of income. We need to get it back. How we can get this back is we apply the actuarial discounting, which is NEX. I think it's better than integration, or because you can integrate if you want A bar X plus N, and then you go back. But this way, it's I think it's straightforward. It's very easy, right? This one should be very easy, right? So this is the actuarial discounting factor. You multiply it by the annuity that starts at x plus n. So this is very, very easy. I mean, you can, yeah, let's take example quickly. Let's take exponential now. Let's say x is exponential. You need mu is 5%, let's take. Delta is 10%. And the question is, we wanted to find 10. Let me take more space. We have A30, 10. So we need, again, like the 10, it tells us is deferred for 10 years for an individual at age 30. With the bar, it says it's continuous. And this one, we can apply just straightforward the rule up here, 30. And then we have A40. Right? So this is exponential. So and this one will be the discounting factor. This one, you can write it NPX. And then VN. Right. So this one, or in, because we have exponential E minus delta N, right? So this one will be easy to write it because we have both of them with E and PX is with the mu. So this will be minus 0.15. Add these together, multiply by 10. Then A40, remember this one, we for exponential is 1 over mu plus delta. And this 1 over 0.15, right? It's so straightforward, it's so easy. And this one will be 1.4875, the annuity for this distribution. But usually question like this will not be as straightforward as this. If I would ask you a question in exam, or if you're writing actuarial exam, usually you need to play a little bit with it. And usually we need to recognize the relationship, you know, between, you know, like the different types of, you know, deferred annuity, temporary annuity, and life annuity. So you are, if you are at age X, you have AX is here, right? It's evaluated at age X because X here, the age, it's the age of evaluation. Then it gives 1 at the beginning of the year. Why? Because it, not at the beginning, sorry, 1 paid continuously every year. Because we're using the bar, so the continuous case. And now up to the period N here, right? So this is AX, that 1 here. Now you can also get evaluated at X for N period, right? Again, the year of evaluation is X, so we all at the same level. This one will give here 1, 1, and then 0. So up to this period. Maybe I'll use different color here. The stream of income, that is this $1 is paid continuously. Right. You can also have one that at AX plus N evaluated at here. So it's sorry, this is X plus N. It's evaluated at X plus N, right? This will give you 1, 1, 1, 1. Now, if we want to relate them together, and this very important relationship, then we have those are at the same level. AX equal AX N. These are evaluated at the same year, at age X. We need to add, but this one, A, evaluated at X plus N. So you see the ones in red, they add to the 0, it give you the blue one. The only difference here that for this guy, the red one, we need to get it back. So how we get it back actuarially is NEX. And this is very important, very, very important relationship. Very important. And as I said, you know, questions would not be straightforward. Let's take one that is a little bit interesting question. That it was a question in one of the Actuarial Society of Actuaries exams. So what is given here to us that mu is constant and well, let's write it this way. Mu is constant 0.01 for t between 0 and 5. And if t is greater or equal to 5, the question gives you a different mortality. Mortality increases. And this is logical. Sometimes, like you have a situation like you have a different mortality for different phase of life. And delta here is given to us in the question 6%. The question here tells us to find x. The solution provided in Society of Actuaries is that they did integration for this one, but I would rather not do it by integration. If I visualize it this way and I know this relationship, then I can solve it without doing any integration. Why? Because ax here, or let's draw one line here just so you have x plus n. Mortality here is 0.1. Mortality here is 0.2. Let's give 1 to the mortality to remember, and this double 1 here to remember. I don't want to put 2, it will become square, so I put double 1. Right? So now if you recognize that this relationship, and we split it here, we split ax into a temporary annuity for period of, instead of n now, how many years we have? It's 5 years. Let's remove it to 5. For 5. And then we add to it ax plus 5. But because we need to bring it back, we need to have 5ex. Right. I want you to see now which mortality we'll use, 1 or 2. This one, the first one, obviously we're going to use mortality 1. Let's give it 1. The 5ex is still here in x, so we use mortality 1. X plus 5, we need to use mortality the 2 line. Let me use different color so you know what I mean. So we'll use the mortality 1, mortality 1, mortality 2 here. So list 1, and this is double 1. And now let's do this one. Take 1 by 1. This is ax. Let's take this one now. This one, if we can take this one, it will give us, now we can use another time the relationship between, let me use this one. We'll use ax, right? And we subtract from it now. We need to subtract from it, similar to this relation, ax. If you subtract from it 5ex, ax plus 5. And now because we are dealing with mortality 1, everything here using mortality 1, right? Because we're operating here. We're tricking this like using this trick that to calculate what we need here. So now this is ax using mortality 1. If you use mortality 1, ax is simple. You remember in exponential distribution is 1 plus mu plus delta, which is our mu is 0.1 plus delta is given to us by 6%. We subtract from it 5ex, e minus, again the same deltas, 0.7% multiplied by 5, then multiplied by 1 over Now the same, because we operating on that is with the temporary, with the annuity, with the mortality one. This one will be also the same thing. If you do your calculation on this one, let's do that. You have 1 minus E minus 0.7 multiplied by 5. Everything divided by 0.7. But I got this number, hopefully it's correct, 428. Let me double check that I got this one correctly. I definitely didn't solve it. Yeah, so this one I got 4.2187. Now what else we need? So we got this one, we need this one. Well, I mean, we can do it quickly here. So 4.2187 plus this, we still need to use the mortality, because you need the first mortality, because to pass the first 5 years you need to use the first mortality. So E minus mortality plus interest 1 plus 6.07% multiplied by 5. Now for this one, 1 over the second mortality, so 2 plus 6, 8%. Now let me do this one. Oh, this is sorry, 7% I meant. If you calculate everything, I calculated everything because I keep it in my calculator, the answer will be 13.27. So this one will be 13.027, the answer. Again, this one is a little bit tricky because you have 2 mortalities, so you need to calculate the first term using the first mortality. And how we calculate the first term? Simply we use the relationship, this one more time, but using the first mortality, and the second one is easy as well, but we need to make sure to use the second mortality. All right, so this is not a very difficult question, this is not a straightforward question, but this is the kind of questions you should expect in the midterm exam, sometimes even a little bit harder. Yeah, so let's take another concept here. Now imagine what we call let's take what's called guaranteed annuity. Now imagine that you have x plus n and forward. Imagine that this period here there is an annuity certain, and what we mean by annuity certain is an annuity payment stream of income that is not conditional on life. So even if the person passes away, they still, the state, they still continue to collect this annuity. So, and many times, many insurance products in many countries, I worked in Malaysia, also like to create this kind of product that you create for the employee provident fund, because if somebody saved for all their life and then they die in the first year without collecting anything, it's not fair. So we try to introduce a product that will give for 10 years at least a certain annuity certain, and after that becomes life. But we need to evaluate it at the time x here. The year of evaluation at time x. This one has a different notation here. But if you want to write y, this one the y, the variable, you will have a certainty. It's certain for n. It's not t. It's certain if death happens less than t. Right. If death happens greater than t, then you will get a deferred life, will get a life annuity, which is deferred. We'll see it. Now, if you want to calculate this, the expected value of y, it has a special notation. Let's calculate it at this period here. It has a special notation that is A. So A, we know it's annuity. Bar on A, we know it's continuous. Now X, the year of evaluation is at X. 2 dot. Now N, there is an N year period, but if you keep it this way, then it's term. It's not term. There is another line here on top of everything. There is another line here. Right. This the other line here, the one on top of X and angle, this tells us that this is guaranteed for N year. This is guaranteed for N year. And this can be written also A. If you take the expected value of a certainty is still certainty, right? Anything is certain. You multiply it by 1. It's 100% it will happen, right? From the term it's certain, so you don't need to multiply with any probability. But for the second term, the AT, if you remember this deferred annuity, it's N deferred for an N period. Now for evaluated, because we're evaluating at age X here, right? But this can be also written, you can write it also A certainty N plus NEX AX plus N, right? Let's take, right? So those formulas, all of them, you need to memorize them. They actually, there is a logic. Too many formulas, but there is a logic. There is a logic for the notation, and there is a logic for the formula. You can always, remember them when you understand them. If you don't understand them, they become confusing. Let's take one example here. So X is exponential. And for exponential, we need mu is 5% and delta is 10%, let's say. The question here is tell us to find A 30, 10, and there is a bar on top of it. And we understand it. We understand this notation, what it means. It means for a life at age 30 will receive 10 years as a certainty, and after that it will be life annuity. So at the certainty, the first one is, doesn't matter the age, it matters that for 10 years you will get this value. And then after that you will have, at age 40, you will have, at 40, you will have an life annuity. But because we need to discount it to today, we use the actuarial discounting factor, which is DEX. Now let's take the A one by one. This is we don't use mu here. Mu is not, the force of mortality is not needed. It's just simply annuity certain, which is for 10 years divided by, this is annuity certain. There is nothing like calculated quickly. 1 minus E raised to 1. .321. And numbers should make sense. Imagine if you're calculating this one and you got it 0.21. You know that it's impossible for 10 payments to give you less than 1. So you need to, make sense, the number makes sense. At discounting it at 10%, it makes sense to have this number, around this number, right? And then the second term here, what we wanted is, let's take them all together, these guys. So 10E30 A40. For 10E30, this is now, we need to raise with adding the mortality with the interest. So mortality is 5, interest is 10, is 0.15. Then before 10 years, because it's exponential distribution, we're using this NPX. And then A40, this, remember, it's exponential distribution. By now we should know this quickly. Is 5 plus 10% is 15%. Let's do that. So now we have A minus 1.5 divided by and then you add, now you add this to the 6.3278. So this one, now you add them up, it becomes to me 7.8087. Right. So now we finished the continuous cases. Next session we'll look at discrete cases. Instead of payment are paid continuously, we'll look at payment that are paid at the beginning of the year, and later on we can alter it to the end of the year. So we're good with this session.